Section 6 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 1. Edited by Francis Rolt-Wheeler. Astronomy. Chapter 5. The Law of Gravitation. When the astronomers of old tried to account for the apparent motions of the heavenly bodies by complete systems of epicycles, they must surely have asked themselves, why do the planets move so regularly? What makes them move thus? If they did, they troubled themselves but little to answer the inquiries in anything but a perfunctory way. For the most part they were content to regard the stars as the playthings of divinity, and the cause of their motions, therefore, as a mystery forever veiled to human eyes. Still one astronomer, Anaxagoras, did have some idea of a force which holds the planets in their orbits, and which might be the same as that which operates upon substances at the surface of the earth. After his day, possibly 499 to 427 B.C., the idea seems not to have been expressed by anyone until the awakening of science in the 17th century. Then Kepler darkly hinted at some attractive force, because his discovery of the mathematical curve described by the planets seemed to demand the existence of some constantly exerted controlling force, and also because he had read Gilbert's De Magnete, in which he was made acquainted with the phenomena of electrical attraction. Such a force as he had in mind would act to maintain the motion of the planets and to drive them along in their orbits. But this was hardly the solution of the problem, since, as Galileo found, the motion of a body itself must continue indefinitely unless there is some cause at work to alter or stop it. This formed the first and most important of the laws of motion which, if not independently discovered by Newton, were subsequently to be stated by him with greater force and conciseness. The laws were of primary importance, because they afforded a new and correct way of considering not only the underlying reasons for the motions of the planets, but of all mechanical problems involving matter and motion. Aside from the three great laws of planetary motion established by Kepler as the result of many observations, the most important lesson taught by him, and one that was readily learned by Newton, was that the motions of the planets were not to be attributed to the influence of mere geometrical points, such as the centers of the old epicycles, but to the actual presence of other bodies. Kepler suggested, in particular, that the planets might be considered as connected with the Sun, and therefore as sharing to some extent the Sun's motion of revolution. From the Sun emanated that special kind of influence which he assumed. Yet, while Kepler considered the Sun as the source of this hypothetical force, he believed in a more general gravity or attraction between bodies. He was unfortunate enough, however, to conceive of it diminishing simply in proportion to the distance between the two bodies, a mathematical impossibility, as was demonstrated by Newton. This is the more surprising as he had demonstrated that the intensity of light was reciprocally proportional to the surface over which it was spread, and that it varied inversely as the square of the distance from the luminous body. It was also unfortunate that, while Kepler's ideas of the nature of gravity were sound and accurate in many respects, they bore no particular logical connection either one with another or with his theory of planetary motion. They are, however, worthy of comment as indicating the situation before Newton took these and other speculative ideas, and the three isolated laws of planetary motion, and bound them together into one beautiful doctrine which must underlie all astronomical science. Kepler, in his work Commentaries on the Motions of Mars, definitely states that gravity is a corporal affection, reciprocal between two bodies of the same kind, which tends, like the action of a magnet, to bring them together. When the earth attracts a stone, the stone at the same time attracts the earth, but by a force feebler in proportion as it contains a smaller quantity of matter. He then proceeds to state that if the Moon and Earth were not retained in their respective orbits by an animal or other equivalent force, the Earth would mount toward the Moon 1/54th part of the interval which separates the two, and the Moon would descend the 53 remaining parts, supposing it to have the same density. This idea of gravity, according to Kepler, was indeed general and served to explain the cause of the tides, as is clearly indicated in the following passage: If the Earth ceased to attract its waters, the whole sea would mount up and unite itself with the Moon. The sphere of the attracting force of the Moon extends even to the Earth and draws the waters towards the torrid zone, so that they rise to the point which is the Moon in the zenith. After Kepler had promulgated his famous laws of planetary motion, many minds independently conceived a force to account for the remarkable uniformity of that motion. Thus the idea occurred to Robert Hooke, to Christopher Wren, and perhaps to Edmund Halley, who was Newton's most intimate friend and who probably did more than any other man of his time to popularize the idea of universal gravitation. It remained for the towering genius of Sir Isaac Newton (1643 to 1727) to formulate into a mathematical law of gravitation the effect of that universal force with which every schoolboy is now acquainted. The honor of having anticipated Newton was claimed by Hooke, and the two entered into an acrimonious controversy. Hooke never brought forward convincing proof of his claims. So far as Newton is concerned, the great merit of his work lay not so much in conceiving the law of gravitation as in his brilliant demonstration of its truth. Starting with Kepler's laws of planetary motion, he showed not only that they were true, which was hardly a task of merit after Kepler had considered the observations of Tycho Brahe and all other astronomers whose recorded observations would throw any light on the subject, but why those laws were true, and why no other laws could have accounted for the conditions actually observed in the motion of the planets. And furthermore, underlying these famous planetary laws he discovered must be the attraction of gravitation. By a mathematical analysis unrivaled in the history of astronomy he proved his theorem completely. Not only did he suggest, as did Kepler, that the power of attraction resided in the Sun, but he proved mathematically that as a necessary consequence of that attraction every planet must revolve in an elliptical orbit around the Sun, having the Sun as one focus, and that the radius of the planet's orbit must sweep over equal areas in equal times, and that in comparing the movements of two planets it is necessary that the squares of the periodic times be proportional to the cubes of the mean distances. These facts were discovered by Kepler. They were explained by Newton, with the aid of the powerful and celebrated mathematical reasoning which he had created. The explanation was the law of gravitation. It occurred to Newton that if a diagram of the path of the Moon for any given period, say 1 minute, be made, it would be found that the Moon departs from a straight line during that period by a measurable distance. In other words, the Moon has been virtually pulled toward the Earth by an amount that is represented by the difference between its actual position at the end of the minute and the position it would occupy if it had moved in a straight line, which according to Galileo's law of motion it should follow unless some external force deflected it. By measuring the amount of deflection he had a basis for determining the amount of the deflecting force. This deflection Newton found by his calculation to be 13 feet. Obviously the force that acted on the Moon made it fall toward the Earth a distance of 13 feet during the first minute of its fall. Galileo had shown that the rapidity of a body's fall to the Earth increased at a uniform rate, what is now termed the acceleration of gravity. In other words, the higher the starting point of the fall, the greater would be the final velocity. Hence, the amount of the attracting force is in some way related to the distance between the two bodies, a relation which Newton expressed by stating that the falling body is attracted to the Earth by a force which varies inversely as the square of the distance between them. If the attracting force then varies inversely as the square of the distance, would the Moon drop toward the Earth at the calculated rate of 13 feet in the first minute? That was the problem which presented itself to Newton. The mathematical solution was simple, based as it was on a comparison of the Moon's distance with the length of the Earth's radius. Unfortunately there were no accurate dimensions of the Earth available when Newton made his first calculation in 1666. Hence he found, on the basis of the erroneous data at his disposal, that the Moon fell toward the Earth 15 instead of 13 feet during the first minute, a discrepancy so great that he dismissed the matter from his mind. When in 1682 his attention was called to a new and apparently accurate measurement of a degree of the Earth's meridian made by the French astronomer Picard, he attacked the problem anew. As he proceeded with his computation it became more and more certain that this time the result harmonized with the observed facts. So completely was he overwhelmed that he was forced to ask a friend to complete the simple calculation. When the computation was ended it was known that the force which causes bodies to fall to the Earth extends outward to the Moon, and that by reason of this force the Moon circles around the Earth. It required but a slight stretch of the imagination to assume that a force which can span the distance between the Earth and the Moon may also span the distance from the Sun to the Earth and the other members of the solar system. That such is really the case, Newton proved by a mathematical calculation of the orbital motions of Jupiter's satellites and of the various planets. These discoveries and fundamental principles, enunciated by Newton, were elaborated with great exactness in his Principia, and the section which discusses the motions of the Moon, confessedly one of the most difficult problems in celestial mechanics, has been termed by Sir George Airy the greatest chapter on physical science ever written. That it has stood the test of time is demonstrated by the fact that Newton's results have scarcely been extended in the centuries which have elapsed since their publication. The entire work is a marvel of exact mathematical reasoning by the greatest genius the world has ever produced, according to Lagrange's estimate of Newton's intellectual powers. Galileo had experimentally shown before Newton that the rate at which two bodies fall to the ground from equal heights is independent of their weights. A mass of gold and a mass of lead, although of unequal weight, reach the Earth at the same time, if dropped simultaneously from the same height. Newton repeated the experiment very exactly. He realized as a result that weight, gravitation, is constant. Because a pound of lead weighs less than 2 pounds of lead, in other words is attracted with 1/2 the force, merely for the reason that it contains less matter, he was forced to the conclusion that gravitation is dependent upon quantity of matter as well as distance. Thus he introduced the very difficult conception of mass as distinguished from weight, or the force of attraction exerted on it by the Earth. The former, of course, is absolute and constant, but the latter varies with the position of the material in question on the Earth's surface or elsewhere in the universe. If the mass of Venus is 7 times that of Mars, then the force with which the Sun attracts Venus is 7 times as great as that with which it would attract Mars, if placed at the same distance. And therefore also the force with which Venus attracts the Sun is 7 times as great as that with which Mars would attract the Sun if at an equal distance from it. Hence, in all cases of attraction, the force is proportional not only to the mass of the attracted body, but also to that of the attracting body, as well as being inversely proportional to the square of the distance. Gravitation thus appears no longer as a property peculiar to the central body of a revolving system, but as belonging to a planet in just the same way as to the Sun and to the Moon, or to a stone in just the same way as to the Earth. Moreover, the fact that separate bodies on the surface of the Earth are attracted by the Earth and therefore in turn attract it, suggests that this power of attracting other bodies, which the celestial bodies are shown to possess, does not belong to each celestial body as a whole, but to the separate particles of which it is composed, so that, for example, the force with which Jupiter and the Sun attract each other is the result of compounding the forces with which the separate particles making up Jupiter attract the separate particles making up the Sun. Thus is suggested finally the law of gravitation in its most general form. Every particle of matter attracts every other particle with a force proportional to the mass of each and inversely proportional to the square of the distance between them. When Newton completed his Principia, astronomy became in the fullest sense an exact science. Given the positions, velocities, and motions of the Sun, Earth, Moon, and other planets, then the manner in which they interact on one another can be learned, and even their form and dimensions determined. In short, astronomy, from a more or less mystical science, became in earnest a mathematical science. When the motions and orbits of heavenly bodies were once observed, the positions of these bodies could be computed for future epochs. In his Principia Newton confines himself to the demonstration of the laws of gravitation. He says nothing about the means by which bodies are made to gravitate toward each other. His mind did not rest on this point. He felt that gravitation itself must be capable of being explained. It is known that he even suggested an explanation depending on the action of an ethereal medium pervading space. But with that wise moderation which is characteristic of all his investigations, he distinguished such speculations from what he had established by observation and demonstration, and excluded from his Principia all mention of the cause of gravitation, reserving his thoughts on this subject for the Queries printed at the end of his Optics. The attempts which have been made since the time of Newton to solve this difficult question are few in number and have not yet led to any well established result. Section 7